Hi everybody. So in this video, we're going to look at invariant points in transformations. So if a transformation maps some point P with an x and y coordinate onto itself, then P is said to be an invariant point of the transformation. And we can see this through this matrix equation. We have our transformation matrix, which we apply to the object with coordinates x, y. And when we apply the transformation, we get the coordinates of the image. And you can see in this example, the coordinates of the object and the image are equal. They're both x, y. So as we progress through the video, we're going to use this equation. And the origin is also an invariant point under any transformation that can be described using a matrix. This is because any transformation multiplied by 0 will always give 0. And this property helps us simplify the more complicated questions later. So as an example of invariant points, the point with coordinates 6 and -2 remains unchanged when transformed by the matrix given here. If we were to multiply this out, we can see 2 lots of the 6 plus 3 lots of a -2 will give us 12 take away 6, and then we multiply the second row by the column, so we get -6 minus 2 lots of -2, and -6 plus 4 does make -2. So you can see the coordinates of this image are equal to the coordinates of this object. Hence, 6, -2 is an invariant point under this transformation. Okay, so if we look at example 1, we're told that T is given by this 2 by 2 transformation matrix, and we've been asked to show that -3, 2 is an invariant point under this transformation. So if we apply the transformation, -1, 2, -3 and 4, to the coordinate of the object, -3 and 2, we should, if it's invariant, get the same coordinates for our image of -3 and 2. And we can check this works by multiplying these matrices. We've got -1 times the -3, and -3 times +2, which gives us -3. Then we've got the 2 times the -3, which is -6, and the 4 times the 2, which is 8. And this gives us +2. So you can see the coordinates of the object are the same as the coordinates of the image. The point -3, 2 is an invariant point under this transformation matrix. Okay? In our next example, we're going to look at invariant lines. So an invariant line under a transformation is a line that after the transformation is applied, maps onto itself. In other words, while individual points on the line might move to new locations, they remain on the same line. So if this is our object, and we apply the transformation, and it's mapped onto this point to create the image, you can see the object and the image lie on the same straight line. So this line would be invariant. The same as here. If we have this object, we map it onto this image, this line would be invariant. And we can use these in our next example. So we've been asked to find the equations of the invariant lines of the form y equals mx, where m is our gradient, of the transformation given by this 2 by 2 matrix. So the way we go about this, we apply our matrix transformation to the coordinates of our object, and the coordinates of our object lie on the line y equals mx. So for our y value, we have mx. And this will equal to the line that the image falls on, and we'll call this big X and big Y, where Y is equal to mx. What we're going to do is we're going to find this big X in terms of little x by multiplying these matrices. We'll do the same for Y in terms of mx. Then we'll substitute each of them into this equation. So we'll find big X. This will be 3 lots of X plus 4 lots of mx. We'll find big Y. This will be 9 lots of X minus 2 lots of mx. Then we'll substitute each of these expressions for X and Y into this equation. So 9x minus 2mx will equal the gradient n multiplied by big X, so 3x plus 4mx. We'll expand out this bracket, so 9x minus 2mx will equal 3mx plus the 4m squared x. Now we can see we can divide both sides by the x term, and these will cancel. So we have 9 minus 2m will equal 3m plus 4m squared. Now you can see we've got a quadratic which we can make equal 0. So 4m squared plus 5m minus 9 will equal 0. And we can solve this quadratic on our calculators. We go to menu, we'll go to the equation solver, we'll choose 2 for polynomial to the second degree. The coefficient of m squared is 4, the coefficient of m is 5, and the coefficient and the constant is -9. So we can see that m is equal to 1 and m is equal to -9/4. So now we've worked out our gradients, we can substitute these values back into here. So the two invariant lines will be y equals x and y equals -9/4x. Okay? Let's try one more example. Okay, so in this example, we've been given that T is this 2 by 2 matrix, and this represents the linear transformation M. We've been asked to prove for the linear transformation M that there are no invariant lines. Well, we know if there are invariant lines, this will be in form y equals mx plus c. And for there to be no invariant lines, we need this m value, this gradient, to not exist. If the constant doesn't exist, then it passes through the origin. But if the m doesn't exist, there is no line. So we need to show that this m cannot exist. So we'll apply the transformation 3 to -1 and 4 to our invariant line x and mx. We don't need to worry about this constant because this doesn't determine whether the line exists, only the gradient does. So we'll leave it in mx, and then for our image we'll have big X and big Y. So now we'll multiply out these matrices. We've got the first row times the first column, so 3x minus mx will equal big X. And then the second row times the first column, so 2x plus 4mx will equal big Y. And then we'll substitute each of these into this equation. So 2x plus 4mx will equal m multiplied by the x term, and then we'll expand out this bracket. So this will be 3mx minus m squared x. We'll divide 3 by x. So we've got 2 plus 4m will equal 3m minus m squared. And then we can make this quadratic equal 0. So m squared plus m plus 2 will equal 0. And then we can use the discriminant to show that this has no real solutions. So b squared would be less than 4ac. Well, b squared is 1, and this 4 times 1 times 2. So 1 is less than 8, So therefore, there are no real solutions for M, which means we don't have a gradient, which means we can't have any invariant lines. Okay? Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe, and you can download the full lesson and worksheet from my website, mrmathematics.com. There's a link in the description below.